So let's find the inflection points for this function f of x equals 3e to the negative x squared. To do that, we're going to do this algebraically, and we're going to find the first and second derivatives. So for this first derivative, f prime of x, that's going to be 3 times e to the negative x squared times the derivative of negative x squared, which is negative 2x. And when I clean that up, I get negative 6x e to the negative x squared. And so that's the first derivative. Now, we need the second derivative. So this is now a product. And we have this u and this v here that we'll have to run through the product rule. And then we'll write out the derivative of this thing. So let's go ahead and do this. When u is 6x, that means u prime is negative 6. And when v is e to the negative x squared, we already know the derivative of that because we just did it without the 3. That's going to be v prime, v prime is going to be negative 2x e to the negative x squared. That means our second derivative, if we run through the product rule, is going to be u v prime. So that's going to be positive 12 x squared e to the negative x squared plus vu prime, which would be minus 6 e to the negative x squared. And we can clean this up a little bit. We can factor out a e to the negative x squared, and we can factor out a 2. So that leaves us with 6x squared minus 3. 6x squared minus 3. So as I mentioned, for a fraction to equal 0, we really just need to set the numerator equal to 0 and solve. And that's what I'm going to do here. I'm going to immediately divide this 2 off. And now I just have to solve 6x squared minus 3 equals 0. That leads to x squared equals 3 over 6, which is 1/2. And when I take the square root, I get plus or minus the square root of 1 over 2, which is going to be 1 over the square root of 2, which is the square root of 2 over 2. So my x coordinates are positive and negative square root of 2 over 2. Now, we really do need to make sure that those are inflection points, so what we need to do is test our second derivative out at points in between those two. And remember, our second derivative was this numerator divided by e to the negative x squared, right? So let's just put that back in. We're testing out this 2 times 6x squared minus 3 over e to the x squared, right? It was negative, I moved it down. So we have to plug some value in that's in between these two. I'm going to plug in 0. And I also have to plug in one that's bigger than the square root of 2 over 2. Oops. Shoot, I'm having trouble here. Come on, man. All right. One that's bigger than the square root of 2 over 2. The square root of 2 over 2 is like 0.7 something. So I'm going to put a 1 in and a negative 1 in. And when I plug 0 into this thing, I get negative 6 over e. Over 1, excuse me. E to the 0 is 1. So that's negative. So this thing's negative in here. It's concave down. And when I plug a 1 in here, I get 6 minus 3. So I get positive 6 over e. 6 over e is positive. So that's concave up. So this guy's an inflection point. When I plug a negative 1 in, it doesn't affect it because I'm squaring it. So those are also positive. So that's concave up. So both of these guys are inflection points. The last thing we need for this problem, I want to find the x and y coordinates. So I need to plug both of these values into the original function so I can figure out the ordered pairs. And the original function was 3e to the negative x squared. So let's plug in, it doesn't really matter. The y values are going to be the same for both these because when I square these two values, I get the same positive. And when you square these, you get 1/2. So this is going to be 3e to the negative 1/2, which is 3 over the square root of e. So those are going to be our y values. So if you're writing these out as exact values, you want negative square root of 2 over 2, comma, 3 over the square root of e, and square root of 2 over 2, comma, 3 over the square root of e. This is how you find these things algebraically. Let me just show you real quickly how we can actually also locate these points with a graphing calculator tool. Spit it out, man. All right, here we go. One more slide. So if we want to find the x coordinates, the inflection points, you can simply type in the function like I have here, f of x equals 3e to the negative x squared. And then you can tell Desmos to graph the derivative by typing y equals, and then f double prime. And to do that, make sure you hit the shift key on this keyboard here. F double prime of x. So you got to do parentheses, x, parentheses. And these places where the second derivative, which is the black curve, cross the x-axis, those are the x-coordinates of the inflection points. If you want to know the y-coordinates, you'll have to draw vertical lines up from those points. So they were at negative 7.07 and positive 7.07. So if I just put in vertical lines here, I could do negative 0.707. And that point right there, 1.82, that must be 3 over square root of e. And then if I put one in at x equals positive 0.707, oops, that must be the other inflection point. So you can kind of see how the curve is changing from concave up to concave down at those points. So where the second derivative crosses the x-axis, that gives you the x-coordinates of the inflection points. If you want to know the y-coordinates, you need to find out the function values. And one way to do that is to draw vertical lines from your inflection points up to the graph. So there's another way to locate those inflection points. Notice, though, that these answers are decimal approximations. And if you need the exact values, you'll have to do it algebraically the way we did it earlier in the earlier in the video. Having said all that, I'm going to end this thing and wish you luck on your math. And if you need anything, you know where to find me. Take care.